Welcome back! Today we'll be looking at 3 new trig graphs, but don't worry, they're more familiar than you think. In this lesson, we will revisit the 3 reciprocal trig functions: cosecant, secant, and cotangent. Earlier in this unit, you learned how to define each of the reciprocal functions in terms of sine, cosine, and tangent. Do you remember how to define cosecant, secant, and cotangent? 1 over sine is the cosecant function. 1 over cosine is the secant function. And 1 over tangent is the cotangent function. Just like with sine, cosine, and tangent, we will begin to graph these reciprocal functions by using a table of values with key inputs from the unit circle. Pause the video and fill in the y values on your guided notes. You can use a decimal approximation if needed. Double-check the values in your table. It's okay if you rounded to a different decimal place. Recall that sine, cosine, and tangent are periodic functions, or functions that return to the same values at regular intervals. What does this mean for the values of the reciprocal functions? Right, they are also periodic and will continue to repeat the pattern infinitely. You might have noticed, similar to when we learned about the tangent function, we saw some values for which our reciprocal functions are undefined. What is happening here? These values are undefined because reciprocal functions are rational functions, and in a rational function, when the denominator is 0, our function is undefined. So, for example, since the cosecant function is 1 over sine, whenever sine is 0, cosecant will be undefined. In the space provided in your guided notes, record a general statement to describe when the reciprocal functions secant and cotangent will be undefined. Pause the video now. When cosine is 0, secant is undefined, and when tangent is 0, cotangent is undefined. Let's see what this means for the graphs of our reciprocal functions. The first graph you drew in the pre-video activity was the sine function. Using the sine graph in your guided notes, let's draw in the vertical asymptotes for the x values that make cosecant undefined. What points will those be? Right, all the x-intercepts or zeros of the sine function. Pause the video and do that now. Make sure you have vertical asymptotes at x equals negative pi, 0, pi, and 2 pi. Next, let's use a table of values to plot some points for the cosecant graph. Pause the video, complete the table of values for pi to 2 pi, and then plot the points from the table onto this graph. What do you notice about the values of cosecant in relation to the sine function? I notice that the minimum point of the cosecant function is the maximum point for the sine function, and vice versa. What will the function cosecant do between x equals 0 and x equals pi as it approaches these asymptotes? Well, as the function approaches these asymptotes, the values will approach positive infinity, creating this curve shape. What will happen as the function approaches both of these asymptotes? Right, for this curve, the function will approach negative infinity. Note that, although we use the sine curve as a guide for our cosecant graph, the sine curve is not actually on the graph of cosecant. If you haven't already, complete the graph of the cosecant function by drawing in each curve. Since the cosine curve is a horizontal shift of the sine curve, what do you think the secant graph might look like? Pause the video and complete the table of values. Then graph the secant function on the included cosine graph. Does your graph look like this? Just like before, we have vertical asymptotes through each x-intercept of the cosine curve, and the vertex of each secant curve coincides with the maximum or minimum value of cosine. Finally, each curve approaches positive or negative infinity as it gets closer to the asymptotes. And remember, the cosine curve is just a guide, not actually part of the graph of secant. In the same way that the sine and cosine curves repeat indefinitely, so too will the cosecant and secant curves. This is the fundamental nature of periodic functions. Now that we know what the graphs of cosecant and secant look like, let's identify some of the key features of these functions. Let's start by identifying the domain and range. The domain of cosecant includes all real numbers except every x value where an asymptote is present. Do you see a pattern in the location of the asymptotes? The asymptotes occur at every integer of pi, that is, 2 pi, 1 pi, 0 pi, -1 pi, and so on. To generalize this domain, we can write the domain of cosecant in set notation as all real numbers such that x does not equal n pi, where n is an element of the integers. What is the range of the cosecant function in set notation? The range of the cosecant function is all real numbers such that y is less than or equal to -1. Or y is greater than or equal to 1. In set notation, it looks like this. Pause the video here and define the domain and range of the secant function in set notation. The domain of the secant function is all real numbers such that x does not equal pi over 2 plus n pi, where n is an element of the integers. The range of the secant function is the same as the cosecant function, all real numbers such that y is less than or equal to -1, or y is greater than or equal to 1. Recall that period refers to the length of one complete cycle of the function. What is the period of the cosecant and secant functions? The period of these reciprocal functions is 2 pi, just like sine and cosine. With sine and cosine curves, we measured their amplitude, or the distance between the midline and a minimum or maximum point on the curve. Since secant and cosecant approach positive and negative infinity, neither function has an amplitude, kind of like the tangent function. This also means there are no global minimum or maximum values in the secant and cosecant functions. The last feature we'll define for these two functions is the location of their asymptotes. Use the domain of each function to define the location of the vertical asymptotes. Pause the video now. The asymptotes of the cosecant function occur at x equals n pi, where n is an element of the integers. The asymptotes of the secant function occur when x equals n pi plus pi over 2, such that n is an element of the integers. Since you're already masters of graphing sine and cosine curves, you'll be happy to know that whenever you graph a cosecant or secant function, you'll start by graphing its associated trig function, sine or cosine, and then add in the asymptotes and curves. Check it out. Consider this example. Graph the function y equals 2 cosecant of x. First, identify the transformation. This function is being vertically stretched by a factor of 2. Next, identify its reciprocal trig function. Since cosecant is 1 over sine, we will apply the same transformation, a vertical stretch by 2 to the sine curve to act as a guide for our graph. Pause the video and graph a sine curve that has been vertically stretched by a factor of 2. This is what your curve should look like. Now, pause the video again and add your asymptotes and curves to make it the graph of y equals 2 times cosecant of x. How'd you do? What about this example? Graph the function y equals secant of 2x. Pause the video and try this on your own. Let's see how you did. First, I identified the transformation. This function is being horizontally compressed by a factor of 1/2. Next, I found its reciprocal trig function. This is a secant function, so the reciprocal is cosine. Then I graphed a cosine curve that was horizontally compressed by 1/2, which means my period is now pi instead of 2 pi. Finally, I added the asymptotes and curves, and my graph looks like this. Before we look at additional changes of this horizontal compression, double-check that your asymptotes and curves are all in the right place. Anytime we have a function with a horizontal stretch, the transformation also impacts other features of the function. Look at the graph and see which of these features you think will be changed by a horizontal compression of 1/2. The domain, asymptotes, and period all change when the function undergoes a horizontal compression. Pause the video and see if you can define each of these features for this function. Whenever I have vertical asymptotes on my graph, I know I have restrictions on my domain. In this case, the asymptotes occur at odd intervals of pi over 4. That means the domain is all real numbers such that x does not equal pi over 2 times n plus pi over 4, where n is an element of the integers. The range of secant of x is not changed by a horizontal compression, so the range is still all real numbers such that y is less than or equal to -1 and y is greater than or equal to +1. The asymptotes of this function occur at x values of pi over 2 times n plus pi over 4, where n is an element of the integers. Finally, I can use the graph to see that one complete cycle of this function is completed in a length of pi, or I can use the formula 2 pi over b to calculate the period, which is pi. We have one last reciprocal function to talk about. That's cotangent. Cotangent is the reciprocal of the tangent function. It can be written as 1 over tangent, or, since tangent is the ratio of sine over cosine, cotangent can also be written as cosine over sine. Pause the video and complete the table of values for cotangent. Then, plot the points and asymptotes on the coordinate plane in your guided notes. Using the table of values, I added these 5 points to my graph. Then I drew the vertical asymptotes for values in the table that are undefined. To finish our graph, we'll draw in curves, like the tangent graph. Compare the graphs of tangent and cotangent. What do you notice? The cotangent graph is the same shape as the tangent graph, but it has been reflected over the x-axis and horizontally shifted. Let's define the features of the cotangent function. Pause the video and define each of these features for cotangent. Review your answers with me. The domain is all real numbers such that x does not equal n pi, where n is an element of the integers. The range is all real numbers. The asymptotes occur when x equals n pi, where n is an element of the integers. Finally, the period of the cotangent function is pi. How'd you do? Let's practice graphing a cotangent function. Check out this example. Graph the function y equals cotangent of x minus pi over 2. Then, identify its features. Pause the video and complete this example on your own. Let's see how you did. First, I identified the transformation. In this case, x minus pi over 2 means a horizontal translation pi over 2 units to the right. I like to use the asymptotes when I'm working with a horizontal translation, so the parent function, cotangent, has asymptotes at integers of pi, which would be here. I need to shift these to the right pi over 2 units, like so. With my asymptotes in the right place, I can plot my intercepts halfway between the asymptotes and draw the curves. Does your graph look like this? Now we can define the features. Since the asymptotes are now at odd intervals of pi over 2, the domain is all real numbers, such that x does not equal n pi plus pi over 2, where pi is an element of the integers. The range is all real numbers. The asymptotes are x equals n pi plus pi over 2, where n is an element of the integers, and the period is pi. Did you have these right? Today, we worked with 3 reciprocal trig functions: cosecant, secant, and cotangent. We used the main trig functions sine and cosine to graph cosecant and secant and identified the key features like domain, range, asymptotes, and period for all reciprocal functions. In the additional practice and online practice, we will work on graphing reciprocal functions with multiple transformations and identifying their key features using the functions and the graphs. See you next time! Hey, hey.